In this lecture, we are going to talk about electric field. Now, in school, while performing experiments of bar magnet, we all have seen that whenever we place iron filings around the magnet, they get arranged in a particular way. Yes, they get arranged in a particular fashion like this. Okay. Why do they get arranged in such a way? Because there is a magnetic field present around the magnet, and that magnetic field is represented by magnetic lines, and the iron filings around the magnet arrange themselves according to those magnetic lines around the magnet. Okay? Similarly, as magnets have magnetic field around them, and that field is represented by magnetic lines, the electric charges have electric field around them, and that field is represented by electric lines of force. Now take example that there are two bar magnets and they are placed far away from each other. When they are very far away from each other, they don't interact with each other. Why? Because their fields are not interacting. So they don't interact with each other. But if I bring these two magnets together, what will happen? Their fields will interact with each other, and depending on the poles which are facing each other, either the magnets will attract or they will repel each other. So they will attract or repel each other means they are exerting force on each other. So the magnets will exert force on each other. Then when they will exert force on each other, when their fields will interact, when they will come close and their fields will interact, then and only then they will exert force on each other. Similarly, we can consider two charges. So each charge, as every magnet produces magnetic field around it, every charge is going to produce electric field around it. Yes, suppose I take two charges, plus Q and Q0. Yeah. Now this is the field that is generated by Q around itself, and this is the small field which is generated by Q0 around itself. Now these charges are sufficiently far away that their fields are not interacting with each other. So these charges will not exert, or I can say will exert, a very negligible force on each other. Okay? So if the charges are not coming in the field of each other, they will not exert force on each other. But if I bring the test charge Q in the test charge Q0 in the field of Q, then their electric fields are going to interact, and then they will experience force. Okay? So what is electric field? The space around a charge Q gets modified when a test charge is brought in that region and it experiences a Coulomb force. This region around a charge object in which Coulomb force is experienced by another charge, that region around that, or the region around that charge in which whenever some other charge comes and experiences force, that region is called as the region of electric field around that charge. Okay? Now, the most important thing is that the electric field is always present around any charge. So if you have a charge, you will always have an electric field around that charge. Okay? So it is not the case that if we have a test charge, then and only then we will or the charge will have electric field. Every charge, irrespective of the other charge in its field, it will have its own electric field around itself always. Okay? Mathematically, electric field is defined as the force experienced per unit charge. Per unit charge means force upon charge. Okay? So let Q and capital Q and small q be two charges separated by a distance r. Then the Coulomb's force can be given by 1 upon 4 pi epsilon naught q upon r square into r cap. R cap is the unit vector along the line joining those charges. Now electric field is force per unit charge. Okay. So now both the charges, we have considered two charges, right? Q and capital Q and small q. Both capital Q and small q are going to have their own electric field, irrespective of the presence of other charge. Each individual charge is going to have its own electric field. So let us find the electric field of both the charges. The electric field due to charge Q is given by F upon small q. So just remember that whenever you are finding the electric field for any charge, yes, you have to divide by the other charge. Means I am finding the electric field for capital Q. So in my expression for electric field, my charge which will come here will be capital Q. If I am calculating the electric field for small q, the charge which will come in the expression will be small q. Okay? So the electric field produced by the charge capital Q is Q upon 4 pi epsilon naught r square. What we have done? We have divided the force by the other charge. So this Q goes and this Q remains and we get this expression for electric field. Similarly, if we have to find the electric field produced by this small charge Q, then we will divide by this and the remaining expression will be this. So in general, if I have any charge Q dash, that charge will have its own electric field. Suppose in that electric field I have a point P which is at a distance Rp from this charge Q dash. Then I will have to find the value of electric field at point P due to this charge Q dash. So we can find it this way. It is 1 upon 4 pi epsilon naught. Which charge I am talking about? I am talking about Q dash. I am talking about electric field because of charge Q dash. So here I have to write Q dash upon the distance between that point and Q dash, that is Rp square, and Rp cap is a unit vector along this direction. So you can find the electric field due to any charge at a particular point. Okay? Now, electric field is a vector quantity. So you should also know the direction of it. Okay? So whenever the charge is positive, the electric field always points outward, away from the charge. Okay? And whenever the charge is negative, the electric field is always towards the charge. Okay? That is what you have to remember. And if we talk about the interaction between these two charges, if these two charges are interacting with each other, then what will be the direction of the field? Positive charge is always having field away and negative charge is always having the field towards it. So the electric field will always come from positive to negative. Okay? This is what you have to remember. Now same case is taken here. There is a charge plus Q and we know that this charge plus Q is going to have its own electric field around it. And if point A and point B are the points which are present in the electric field of the charge q. We have to find the magnitude of the electric field at point A and point B. So as we had calculated previously, the electric field at A due to the charge plus q will be 1 upon 4 pi epsilon naught q upon RA square. RA is the distance between point A and charge q. And the electric field at point B due to the charge q will be 1 upon 4 pi epsilon naught q RB square. Yes, q upon RB square. So this is how you can calculate the electric field at a particular point due to some charge. Okay. Now, SI unit of electric field is Newton per coulomb or volt per meter. Now, how this volt per meter has come, that we will see in the next lecture. But Newton per coulomb, we know that electric field is equal to force upon charge. So force unit is Newton and the unit of charge is coulomb. So the unit for your electric field is Newton per coulomb. Okay. Now let us see the dimensional formula. It is F upon Q0. So the dimensions for F are L, M, T minus 2. And charge. Charge is what? We know that current is equal to charge per unit time. Yes. So charge will be I into T, current into time. So the dimensions of your charge are IT. Yes. Then if I take this T here, what will happen? The power will become minus 3 and this I, when it will go up, the power will become minus 1. So the dimensions of your electric field are L, M, T minus 3, I minus 1. Now, here everywhere we had considered that our charges are placed in vacuum. But now let us consider that our charge is kept in some material which is having the dielectric constant K. Okay, dielectric constant is K, and then the permittivity will not be epsilon naught, it will be epsilon. So whenever we calculate the force between two charges, what will be the force? 1 upon 4 pi epsilon Q naught upon R square R cap. Yes. Electric field due to charge Q will be 1 upon 4 pi epsilon. Why epsilon? Because the permittivity of this medium is epsilon. Epsilon Q upon R square R cap. Now, in the place of this epsilon, we can write epsilon naught K, because permittivity of any medium is equal to permittivity of vacuum into the dielectric constant. So we can write epsilon naught K instead of this epsilon. So we get this expression. Now, for if this medium was not present, if it would be vacuum, for vacuum K is 1. So when you put K is equal to 1 here, you will get the electric field in vacuum. If you place your charges in some other medium, you will have the particular value of K. You can put the value of K there and calculate the electric field accordingly.